So, good evening. So, today's topic is shock tube, wherein I am going to discuss about basics, then building from scratch, how to make a shock tube by yourself, then how to perform experiments and how to do measurements, and how to do simulations in a shock tube. So, with this topic I will move ahead. A simple notice that in my slides there will not be any background such that it will not distract you, and then I do not have any transitions in slides, rather I will be focusing on the content since it is a webinar session. So, with this note I am moving forward. Any doubts or clarifications if you have in between the topics or explanations or discussions, experiments, simulations, whatever, you can comment in chat box, and there are people dedicated to answer your queries. They are my students, past students and present students who worked in shock tube and who are working in shock tube. So, here I have to acknowledge few people before moving into the session. So, I thank my professors who taught me gas dynamics and who discussed gas dynamics with me with one-to-one basis at IIT Madras, which helped me really in building setups and also inferring physics from the experiments and the simulations. My special thanks to Aravind and Anugya who came up with the proposal that we want to build a shock tube, and they did this project last year, and they have received admits from Imperial College London, and also thanks to Srinadhi who is their junior. She is presently continuing their work, who extended their shock tube work to Acoustics, and she is also present online. So, these three people are online. They will be helping you in answering the questions. So, what are the takeaway things that you can have from this webinar? So, the basic idea is about telling you how a shock tube is, what is a shock tube, basics of it, and how can you build one, what are the experiments you can try in that, how can you measure something out of a shock tube with associated accessories, and then how to simulate using some generic tool. So, before starting to our topic, I will start with a small story. So, I think almost people like stories, that is where I came up with this. So, I have to introduce the characters of the story. So, I am introducing you two characters. One is Nathan Shah on the right side, you can see, and on the left side Yashpal Velu. These are two imaginary fictional characters I have, and they have their own characteristics. Like Nathan Shah has a strong character, he can force people and get things done, and he is close with his people, and he has a strong follower base. On the contrary, if you see Yashpal Velu, he has easygoing character, he might be helpful to all people. Also, he maintains social distancing like COVID situations, and he has a mixed type of followers. The most important thing which you have to note is these two people are opposite to each other, but all these people have their own ideas which is unique. Now, moving ahead, the story is these people start protesting and roaming around streets with their followers. They get arrested by policemen, and they are confined in a cell. So, this cell, if you see, this is a rectangular cell wherein you find Nathan Shah on right side and Yashpal Velu on the left side with their followers being arrested and confined. And this police officer tells that there are two gates which is on two sides, that is on the left extreme and also the right extreme. So, this information is taken by these two people and their followers. So, there is one more catch here in the story. Out of these two gates, one of the gate is strong and one of the gate is weak. So, the right side gate is weak and the left side gate is strong, let us assume that. And now after knowing this thing from that officer, these people now start planning, and they try to find which is the way to move out. So, this Nathan Shah, he comes up with an idea, okay, let us push and see the wall or the gate, then we will find the way to move out. That is where this person and his group, they start pushing the wall, and they break open it since it was weak. The gates are open, and they try to move forward. And Nathan Shah, since he has a strong follower base, almost all his followers try to follow him in close groups, and some of the Yashpal Velu's group members, they also shift loyalty to that group, and there are few people in the mid confused whether to go this side or that side, and since these people are contrary or opposite to each other, this fellow Nathan Shah is moving towards the right, and this Yashpal Velu, he is telling the group members, okay, this group is going towards right, so let us go towards the left. So tells them to go towards the left to find out way, and their followers are going towards the left, banging on the left gate. It is so strong it could not open, so they return back and tell this person, we could not open the gate. Okay, this person says, okay, you go ahead, I will go and try. Okay, he goes, he bangs on the door, and he also could not open. By this time, Nathan Shah and his associates and some of these followers from Yashpal Velu's group, they move out of the cell and escape. They roam out happily. Then at that time only this Yashpal Velu realizes, okay, we should have gone through that particular route because the gates are open, and we have tried banging on the wall and wasting our energy. Once he gets that idea, then he also tries to move out towards the right. By the way, he has already lost half of his energy towards breaking that left wall, and when he comes out, he doesn't have energy, so that's where he is again caught, something like that. So this story, I think, will give you a brief idea about two characters, and these two characters are related to our main story. This is about a shock tube. So I am going to introduce you to two characters. So if you see this slide, you will be able to see Nathan Shah, which was depicted as a normal shock, and Yashpal Velu as a expansion wave. So Nathan Shah or normal shock, now if you think about the characters of the present story, you will be able to correlate the physics which happened inside the cell. That's where we are going really into the story here. I have to emphasize that normal shock is a property which has a property which has a strong say characteristic. Whatever is passing through the normal shock, it will be decelerated, and also the particles are agglomerated to form a normal shock. On the contrary, if you see expansion wave, it is weaker than normal shock. Also it accelerates the motion of particles, also it is having expansion characteristics. So these two characters of our story, which were correlated with the previous analogy, we will be using these characters or properties in our shock tube. So I hope you had a brief idea of what the story is and what we are trying to understand in the coming slides. So moving ahead, the story is about a shock tube, and I will be defining shock tube here. So basically the definition of shock tube is a device, you can say an experimental device or a test rig, which is tubular in structure, which is used to produce plane propagating shock waves by rupturing a diaphragm that separates a high pressure region from a low pressure region. So that is how a shock tube is defined. So basically a tube which is separated by a diaphragm, wherein you have a high pressure region on one side and low pressure region on other side. If you rupture the diaphragm, a plane propagating shock wave is produced, and that moves towards the low pressure side. So with this definition, we will move forward and see how a shock tube looks like. So I have shown here a typical shock tube as a schematic. So what you are seeing on the left with red color is the high pressure air. So I will be following this color code, high pressure air with red, and low pressure air with blue color, and there is a diaphragm in between. So this is a typical shock tube. So what happens when you have this kind of shock tube and if you move the diaphragm? Let us move to next slide. And here, if I have a closed shock tube, if I start moving this diaphragm from the initial position towards the right, you see from the top to bottom, you might find there is a low pressure region on the right which is getting compressed. So the low pressure is reduced, and you are reaching towards normal pressure. On the contrary, on the left side, if you see, The red is depicting high pressure region, and this high pressure region, as the diaphragm moves towards the right, this high pressure region loses its pressure strength, which means you have a higher volume by moving this diaphragm. That is where your pressure is reducing. That is why I have shown in a color which is fading with respect to the movement of the diaphragm. So, in the last bottom one, if you see, that is the tube where the diaphragm is removed. So, once you remove the diaphragm, the pressure, high pressure and low pressure gases or air mixes together and it comes to a equilibrium state. So, this is a typical scenario. Now, in a typical shock tube, what happens is you rupture the diaphragm and then shock waves and expansion waves are created. So, that we will see in a later stage. So, with this background, if I am a student or a faculty, I want to build a shock tube for my experimentation purpose. How to start and how to build a shock tube from scratch? So, basically first we have to start with a concept of shock tube, a schematic we should come up with. So, here is the schematic I have shown in this slide, wherein a shock tube is designed. It has two sections, a high pressure section and a low pressure section. On the right extreme end, you have this open end shock tube, because the wave has to be sent out. We do not want reflections, that is why I have kept a open shock tube here. And you find a coupler in between say these two tubes which is held tight by bolts, and in between that you have a rubber gasket, and between these rubber gaskets you have a diaphragm. And the left side chamber, which is the high pressure chamber, is connected to an air compressor, wherein from air compressor you can have high pressure gas stored inside the diaphragm. So, that is how it is designed. So, we have designed two locations for keeping microphones, wherein from microphones we can take signals for further measurements and then calculations subsequently. So, having this concept, how to come up with an experimental setup really? So, if you want to come up with an experimental setup, you can design that particular concept into a CAD and then go for testing. So, our group has done testing of this particular design with the given material strength and other properties. So, supplying some boundary condition, testing its for its strength, where all weak joints are there, something like weak points in the domain by using a structural analysis. Once the design is okay, then we have to build this shock tube as a physical product. So, it is not difficult to build a physical product. So, what we decided is we went ahead, found that what are the materials that can be used for these two sections. So, initially we thought about metallic pipes and metallic flanges. Later we thought that the metals will be costly. Why do not we go with plastic kind of material? That is where we thought HDPE kind of material will be fine, which is ultra light in weight compared to metals. And then if you see the strength, it will be of a comparable strength, and if you see manufacturing, machining or fabrication processes, these plastics are always easier to handle. That is why we thought we will go ahead with HDPE material itself. So, basically we have two sections which I have shown made of HDPE sections or HDPE pipes. You will find the high pressure section on the top. That picture shows you the pipe clamped to a wooden plank. On the right side you see a flange. On the left side you find a end cup which is closing the pipe, and there is a valve in that from which you can feed air into this pipe. So, bottom picture shows you the low pressure section which is open to atmosphere. Comparatively I am saying that the section which is on the top will be pressurized with air, that is why I call it a high pressure region. Now, on the bottom picture you can see the low pressure side, which is on the right side of the shock tube, which is open to the atmosphere on the right extreme end. So, that is how we have kept it. So, this pipe is also clamped to this wooden plank, and you might find some wires with two color jacks for connecting to devices, and these two wires are connected to the pipe at a particular location where a microphone is placed. So you find on the left side there is a microphone, on the right side also there is a microphone. These two wooden planks are fixed to a framework wherein you can do some experiments. So what are the other accessories which we need for doing experimentation is, if you see this picture on the left, that is the power source we have, that is an adapter which can power up the compressor. The mid picture is the compressor which you can get it from automobile stores or from Flipkart or Amazon or some other eBay, something like that. And this is for pressurizing automotive tires. So this is available online. And extreme right side you have a picture which shows the pressure gauge. So most vulcanizing shops or automobile garages, they have this pressure gauge. It's a kind of a Bourdon gauge pressure gauge. So you can measure pressure using this. So apart from this, we used one more accessory, that is a dual line splitter, which I will show in subsequent slides, which can take two information from two mics and it can send it to a device which is recording the signal. So the completely assembled shock tube will look like this. So basically we had a framework, that is a metallic framework on which this shock tube is placed and fixed with that frame. And if you see this left extreme side, there is a pipe which is connected to the shock tube, and the pipe is connected to the compressor which can drive the shock tube up to 8 or 9 bar pressure. And if you see this entire setup, this is placed on ground and it was kept at a hanger which had a wide space such that the shock wave can move out of the driven section towards the right extreme end. So we didn't have any obstacles or obstructions on the right extreme side. So we had enough space to move around to work with the shock tube. Also you have to note that when you are working with shock tubes, especially experiments, you have to always wear ear protecting devices like muffler. If you do not get mufflers, at least rolled cotton should be plugged into ears, because the shock waves which are moving out of this shock tube produce noise, and that is a impulsive noise because it looks like a blast wave moving out of the shock tube, and it might damage the diaphragms of our ears. So with that I will move forward to show some of the experiments which our group performed. So the typical experimental setup, the previous setup which I have shown is just for testing the shock tube, like keeping a diaphragm, pump air through that high pressure side and burst the diaphragm to see whether the shock tube is working or not. So that is the trial experiment part. So to go for a real experiment wherein we should measure something and infer some physics out of it, so that is where we came up with this experimental setup, wherein on the left side picture you might see the shock tube with connected pressure gauge that will indicate what is the pressure inside the driver section. So that is the high pressure section. So you can connect this driver section or high pressure section with the compressor and you can keep pumping air, and you can see the pressure gauge which will be showing pressure, that what is the increase in pressure happening in the driver section. So why we should know this pressure inside this section is, like at some particular point of time the diaphragm will not withstand the pressure, so it might burst. At that time the pressure it will be keep on increasing, and at the time of burst the pressure will stick to a point and then come back. So the maximum pressure or the bursting pressure you can directly get it from this pressure gauge. That is why we have connected a pressure gauge in this driver section. So on the other side you have this driven section or the low pressure side, wherein you have two microphones, and the two microphones are connected via wires, and you might find a dual line record splitter which is a single 3.5 mm jack wire, which you can connect it to a recording device like mobile phone or a normal 2-channel sound recorder, and this has two outputs wherein you can take input from two microphones and connect it to this dual line recording splitter. So once we have this setup ready, like keeping a diaphragm between two pipes and completely sealing it, tightening it with bolts, and then we can start injecting air through the left extreme end, that is via a valve, and it is a one-way valve, the non-returning valve. And once we reach the bursting say pressure, of the basically of the diaphragm strength, it will burst and it will produce a shock wave on the right side, and then it will move out towards the open side on the right extreme end. So, if we do one such experiment, what will happen? So, first initially our group tested different diaphragms, which diaphragm will work first for the shock tube which we made. So, initially I told our group that okay, you go ahead with testing different types of papers and different types of sheets which are available from market. That is where our group tried first A4 regular sheet, then A4 bond sheet, and then A3 tracing papers, and then the other things which I have not mentioned here are aluminum foils, OHP sheets, and something similar to that. So, on testing these diaphragms, you might find from the picture the first A4 sheet and this regular sheet and the bond sheet, these two things did not rupture, but a A3 sheet ruptured. You might find that part missing from that picture. So, that is the ruptured part wherein the paper moved out say with the flow. Why this paper thing from regular and the bond sheet did not rupture is, if you see paper, the paper is made up of wood. Wood is ground to a paste state, and then it is rolled into a sheet and then dried up, and it is made as a paper. So, when our group used this particular paper as a diaphragm, when we pressurized air, the air started leaking through the fibers of this wooden strands in the paper, and it started leaking through it. So, it could not withstand the pressure, or it could not hold the pressure exactly to say. So, this is leaking, that is why it could not hold higher pressure and it could not rupture. So, we discarded these as diaphragm materials, and we started working on this tracing paper and other materials which we had, because those materials gave us results. So, moving forward, what we did is, when we did the experiment, we recorded the noise using a mobile phone, and the raw data is collected. If you see this present slide, you will be finding some audio data. So, basically there is one particular line on the top side and the bottom side. So, two channels were recorded, that is from microphone 1 and microphone 2. So, the bottom one is microphone 1 and the top one is microphone 2, and you will not be able to find really what exactly happened in this say audio signal. One thing which you can infer is on the left, from the beginning of time, you might see no audio signal or just a noise, which might be the ambient noise which is recorded, which has the minimal amplitude. So, you find a straight line. Then you have a sudden burst wherein the amplitude is higher, and this is basically indicating the rupture of the diaphragm. So, the microphone which is present near the diaphragm has captured the rupturing of diaphragm, and that is where you find this higher magnitude as a burst. And as you see on the trailing side, the magnitude is decreasing with respect to time. So, in parallel, if you see the audio signal on the above graph, this is from the microphone 2, which is on the right side. So, you find initially 2 or 3 lines as a signals, which is showing the amplitude which is due to the burst of the diaphragm which happened a little earlier. So, there is a small gap, and then again you find a continuous band of audio signal. So, which indicates that there is a wave which moved through the say on the surface of that particular microphone, and before that you had a gap, which means basically this is the time which the shock had taken to move from the microphone 1 to microphone 2. So, if we know what is the time instant at which the shock wave has hit the microphone 1 and what is the time instant at which the shock wave has hit the microphone number 2, we will be able to find what is the time taken for the shock to travel between these two microphones. So, we prepared our driver section, the driven section or the low pressure section with a particular separation of microphones placed on that particular pipe. So we know the separation distance. So basically the distance by time taken, you can calculate velocity. Once you have velocity of the shock, you can calculate the velocity of the sound, and ratio of velocity of shock to velocity of sound will give you Mach number of the shock. So this is how you can calculate Mach number from your shock tube. So basically you have to do an experiment, you have to record signals from your microphone. So this is the least basic say device that you can use to record the signals. Professionally, to do this as an experimental thing, as in a laboratory, as a faculty or a researcher, what you can do is replace these microphones with transient pressure sensors and connect these to a data logger and track all the signals, and then you will be able to find where the pulse or shock happened, and time between those two pulses exactly will tell you what is the shock speed. So basically this is the zoomed in data of that audio form. On the bottom side you might find the peak 1, which is the onset of the shock, that is exactly shock when met, microphone number 1 on the left side. So this is the indication. What we have done is we exactly took what is the maximum amplitude, that is the first instant. We assume that that is the place where the shock is moving over the microphone. On the top audio signal you might find a place where we have mentioned peak 2, that is where the first positive audio signal happened, which means the shock is passing through that microphone at that particular instant. So we basically found where these two peaks happened. There is a timestamp on the top x axis. So we took the timestamp, we found what is the delta t. We know that separation distance calculated Mach numbers, we found it to be around 1.1 Mach. So that is where this basic experiments can be done. So the other experiment which we did is like outside the shock tube on the right extreme end. We placed microphones at different locations to know about the audio levels at different locations downstream the open end of the shock tube, to find how the shock strength decreases with respect to axial distance. So this is the typical graph expressed in terms of percentage from left to right, which shows that from the end of shock tube towards the outer region on the right side. So this clearly indicates that shock strength is decreasing with respect to axial distances outside the tube. So why the shock strength decreases is you have viscous resistance from the air molecules present outside. This shock is also expanding laterally and also moving axially forward. So this might lose strength by overcoming the resistances. So this is one way to infer this graph. Also we want to see how the shock is creating impact. So on the right side you find a picture. Basically what we did is we took a wooden plate and painted it with green color paint and with a thinner such that it has some viscosity which will allow that fluid to move when there is a blow of air. So we tried to impinge this shock on this particular plate. You might find a white region in between wherein we have shown as a zoomed in square. This will show that this is the place where the shock has impinged or shock has met with that particular wall. Also on the left side what we did is we kept the same plate again freshly painted with the paint with the thinner appropriate say mixing combination such that we can trace the flow. So we kept that at the end of the shock tube and we ruptured the diaphragm to see how the shock is moving out of that tube when the shock is interacting a wall, how it will behave. So this is the trace which we are seeing. We have a highest width near the shock tube end, and as it moves it loses energy or it loses its strength, and you might find the width is reducing as you move towards the left side. So this is what you are seeing from the visualizations which we perform. This is very basic thing. Only thing is you have to find out what kind of a combination will work for this paint or oil visualization that you can do. So Basically, you can do experiments, you can do measurements, you can do some visualizations using shock tube. Moving further, so this is a part where Srinadhi worked. She is working presently on acoustics, which is coming out of a shock tube. So the same experimental setup which Aravind and Anugya designed, she took it and she added a silencer or a baffle at the right most extreme end, wherein the shock is coming out of that open end tube, and the same experimental setup with same accessories. Only one more additional thing is used here in this experiment, which is a sound level meter. So the sound level meter you might see on the right bottom corner. That's the place where a sound level meter is placed. If you see literature, you might find people who do acoustic studies, they keep their recording device or sound level meters in this zone for comparison purposes. So this is typically placed there, wherein this wave will not directly impinge on the sound level meter and damage it. So it is perpendicular to the stream, such that when the wave is coming out, the noise will be radiating, and a plain wave of sound will be hitting the sound level meter, and you can record what is the noise level. So what she did exactly is she changed the size of the pore in that silencer or the tube which is attached to the extreme open end of the shock tube, and measured the noise levels and came up with some inferences. So this is the concept of say acoustic measurement using shock tubes for say noise reduction studies. So this is the real experimental setup which she made it in her home. Due to lockdown situations, she could not perform experiments in anechoic chamber which we have built in our college. So despite having all the facilities, this lockdown made us to decide that we will go with experiments in home itself. So thanks to their family members who supported her to perform experiments in the home. So dedicated room was given, the complete experimental setup was kept, and the setup was anchored. Then you might find on the extreme left side there is a noise level meter placed. So the shock tube is connected with this particular silencer, and opposite to the silencer or the open end of the shock tube, the window is kept to open, and the experiments were performed during a time where the ambient noise level is low. So this study was done using this noise level meter over a period of a week, and then found these are the regimes where noise level, the ambient noise level will be less. So basically doing a survey and finding optimum time for experiments. After finding out that the experiments were performed, and she inferred some results from these experiments. So the effect of silencer is shown in this graph, and what we can infer from this, the bottom x-axis shows that the size of the pore or the aperture on the silencer non-dimensionalized with the diameter of the shock tube, that is the flow passing area. And on the y-axis you see a sound level which is shown in decibels. A is for human audible thing. So you might find that as the diameter of the pore is decreasing, the sound levels are decreasing. Or you can see that when the diameter of the pore is higher, the sound levels are higher, which means the noise is propagating out, and it doesn't lose its energy much when the pores are bigger and bigger. So we had done a lot of other experiments by changing the porosity of the pipe and so on, and the articles are under preparation, so we will be coming up with possible outcomes. So this is all about the experimental aspects. Moving ahead, I have some of the results from simulations. So when we do experiments, I think if we have some theoretical calculations and simulation or simulation based results, I think you can compare, and you can gain confidence how far you are doing well with your studies. So that's where we had this simulation aspect. So initially we decided that we can go with the initial design which we had for experimental aspects. the CATIA design, but some of the simulation tools that doesn't really need this CATIA geometry. So what we did is we took a tubular geometry. So I have shown this on the picture on the top, which shows that 2500 mm is the length and 40 mm is the diameter. So it's a circular cross section tube which is depicting the original experimental setup. We don't have flanges and other couplings shown here because computationally we don't need them. We have to separate it as a diaphragm placed inside this tube, which can be done numerically. So that's where we didn't come up with the complications. So the geometry is very simple, and moving forward, whenever we use a geometry in CFD, we have to discretize the geometry, that is dividing the entire domain into smaller and smaller cells, and then you can solve your governing equation in each and every cell inside the domain to come up with physical properties at each and every point of the domain, and then you can do post processing to come up with solutions. And these are the governing equations which govern the fluid flow. Basically, if you want to track any fluid flow, you have to have some basic governing equations which are coming from the conservation laws. So you have conservation laws like conservation of mass, conservation of momentum, conservation of energy, and so on. So in this we have governing equations which are mass conservation equations, momentum conservation equations, and energy equations. This is suitable for compressible flow, and we used OpenFOAM for the simulations, which is an open source tool, and the algorithm which we used is like Pimple algorithm, and there is a dedicated solver for compressible flows, and with this equations as available as a solver in OpenFOAM, we invoked that solver, and with some of the boundary conditions, like you have the pipe, you have to supply with the boundary conditions. So what we essentially did is this boundary condition, the open end, we gave it a zero gradient, which means inside the pipe and outside that pipe the value of pressure, temperature, or velocity will be same. That's where you have the zero gradient condition. The walls are given with no slip conditions, which means velocity is 0 on the surface of the wall, and then there are patch surfaces, like you can fix a particular plane with a particular boundary condition. So patches are used at some locations. Then empty boundary condition, basically we tried 1D simulations and 2D simulations prior to this 3D simulations. So the geometry and mesh which I had shown in the earlier slide are for 3-dimensional simulations. So this last boundary condition we didn't use for this simulation. So after giving the boundary conditions, what we have to do is we have not given this diaphragm and high pressure and low pressure section. So basically we have to tell the computer that the left part, this much length inside the tube, these many number of cells, has a higher pressure. That's how we have to initialize. Once we do this initialization, we can start the solver by saying that at time t equals 0, you can start solving. And with respect to this transient simulation, you might find that the molecules which is present on the high pressure side will start moving say towards the right side, wherein forming normal shock and expansion waves. This can be simulated using various solvers. There are multiple solvers available in OpenFOAM. Basically, if you want to get density based solutions, you have to stick to the solver which gives you density as a result. And this typical picture is a completely post processed picture. On the right side you find timestamps like 0.001 seconds till 0.0005 seconds. So basically you see the first shock tube, you might find the contact surface, a shock wave, and an expansion fan. The shock wave is moving towards the right because that is the low pressure side, and the contact surface is the original place where the diaphragm was there, and which separates the molecules which are moving towards the shock wave and also moving towards the expansion fan. So the expansion fan is weak and it is moving towards the left. With respect to timestamps, as you move from top to bottom, you might see that shock wave is moving towards the right, and your expansion fan is moving towards the left. Also you can see that expansion fan is expanding with respect to space, and you see shock is strength here, and it tries to maintain its strength when it moves towards the right. Also the contact surface, which was exactly on the mid side, started moving towards the shock wave. Basically I have to correlate with the story which I invoked earlier. There are people who are in dilemma. That is what exactly this contact surface is doing. It will be in dilemma for some time, then when the shock wave is stronger, it tries to move along with the shock waves. So this is one particular solution that you can see, which is typically like a numerical Schlieren or shadow graph, which you can extract from this particular data, and this will tell you about the shocks and expansion fans. And this is a typical visualization with respect to time, how the pressure and the temperature varies. So what basically our group did is, the simulation was made to do the transients, and post process recorded as a video and then converted into GIF, and the GIF is played here. At time t equals 0, the shock tube is intact with the high pressure zone on the left and low pressure zone on the right. When we give say simulation, that is iterations, it starts solving, and the molecules from the left starts moving towards the right. That is where you find the pressure on the right side, that particular zone is decreasing, and also the left zone is decreasing, that is the low pressure is also decreasing, high pressure is also decreasing, the pressure gets normalized once the shocks and expansion waves decay or move out. Similarly, you find this temperature effects on the bottom side. You might find that the initial place where I told anything or any material or any gas molecules which passes through the shock wave will have say a higher impact, and it will have a higher temperature. That is where you might find that when the shock moves on the rear side, it creates a high temperature zone, and on the contrary you see the left side, it is basically because of the expansion wave. So this kind of animation also you can try to do in say simulations, which will really tell you how the shocks and expansion waves behave inside a shock tube. The ParaView is the tool which we used for doing all the post processing stuff, and this is also a freeware. So coming to error analysis report of experiments or simulations, we have to check whether we have done things right or wrong. That is where we had a basic check. So what our group did is, exactly in the initial place, we know the formulas for calculating the Mach number in a shock tube from the books and literatures. So we know the pressure which we have measured from the pressure gauge. So we took that pressure from experiments, we have fed through the formulas, and we calculated the Mach number. We came up with Mach number of 1.16. From experiments, that is from the audio recorded in the mobile device via the microphones, the audio signals were processed, and the time separation and the data is taken to calculate velocity of the shock, and then it is converted to Mach number, and that is found to be 1.155. So we also did simulations, right? So the simulations were giving a Mach number of 1.28, and we tried to find out how much is the error when we compare the experimental results with the theoretical results, and also computational results with theoretical results. So we found that experimental results were better, and computational results were giving some error like 10%, but later we came out with some good realistically matching results by tweaking in the conditions, by resolving a lot of errors which we had earlier, and simulations can be done in a perfect way to get solutions with lesser error. The other thing is, when you are doing experiments, you have to find out how far your experiments are repeatable. That is where this graph is showing like this is acoustics or acoustic amplitude on the y-axis. On the bottom x-axis you might see how many number of trials are done for experiment. It's like if you do 10 experiments or 20 experiments at different time instances or in one go or on different days of a week, something like that. So basically you have to try with different combinations and you have to find what is the Mach number or what is the amplitude which we get, and then try to find out the average of that particular series of data which you have and find the standard deviation, and then you can find out what is the percentage of variation. From this you can easily find out that what is the repeatability of your results, which will inflict upon confidence on your results which you get from your own experiments. So we had several outcomes from the project which we have done. So Anugya presented a paper on blasting effects, and Aravind also presented on paper on numerical simulations, and one of their papers got best paper award in the conference where they presented. And there are subsequent articles under preparation for the acoustic part, and there are a few articles which are under consideration which will be published soon. So you can follow our works in Google Scholar or LinkedIn or ResearchGate or whatever site you have. We will be sharing our results. Thank you for patiently listening to my webinar for a period of 50 minutes. I think I have given a brief introduction with a story and then basics of shock tube, how to build a shock tube from the materials available from basic hardware shops or plumbing shops, and with the basic recording devices like mobile phone and so on, and then a brief idea of how experiments can be done, visualizations, and then some flavor of results, and finally with some simulations, some animation, and the results, accuracy and error and so on. I hope people who are young and thinking about project aspects, you can have this as an input. Similar situations can arise for other experiments which are related to this in supersonic aerodynamics. We are always open, and we welcome people to interact with us for collaborative works or discussions and so on. Thank you once again. The session is open for discussions, question and answer.